In this video, we'll discuss related rates. Right? Basically, you are given more than one quantities. All of them depends on time. They are related. So if you are given all the rate of change of all the quantities except one, then you can use the relation to get the rate of change of the unknown one, right? So that's the idea. So let's write down a setup of this this kind of problem, right? Suppose you have x, y, z, or more, right? So that's basically all quantities, some quantities, area, size, volume, many quantities, right? They are depending quantities depending on time. Same, we use t as our time, right? T is the independent variable, right? So basically, we know that x, y, z, or more are functions of time, right? And also, we are given x, y, z, or more are related by equation in x, y, z, no matter how many quantities you have, right? And all rates of changes, rate of change are given except one of them, right? You are given dy over dt or dz over dt, but we don't know dx over dt, right? So our goal here is find the unknown rate of change. Normally, there is only one unknown, right? All the others are given. And what we do here is you are given such an equation here. We differentiate equation about time t using the method we have learned about differentiating functions, right? Consider all the letters as a function of time, right? The independent variable is time. That's very important. So time is the only independent variable. So let's see an example, right? Let's see an example. Suppose we are given two quantities, which y equal to root 2x plus 1. So this is an example. Suppose that, right? And where what? X, y are both functions of t. So if dx over dt is given, which is 3, we want to find dy over dt when x is 4, right? So here we are given two quantities, x and y. Both are function of time, right? We are given the rate of change of x is 3. We are looking for the rate of change of y when x is 4. So we don't have any other approach. You are given such an equation, we differentiate that about time t, then we plug in the information we are given to figure out dy over dt, right? We just solution we just differentiate y equal to root 2x plus 1 with respect. So very important, you need to consider t as your independent verb, not x, right? As t changes, x, y changes, right? We need to differentiate both sides of this equation about time t, right? Left side will be just dy over dt, nothing happens, just easy differentiation, right? The right side, that's a composition of two functions. We need to apply what the chain rule, right? Outer function is square root, you get 1 over 2, 2x plus 1 to the power negative 1/2 times the derivative of 2x about t. So just 2 times dx over dt, right? The derivative of 1 about t, that's a constant, you plus 0, right? So get the rate of change of y. But we are looking for this when dx over dt is 3 and dy over dt, I mean, when x is 4, right? So when x is 4 and dx over dt is 3, then dy over dt, plug in the numbers, right? This is 1/2. You get 2 times 4 plus 1 to the power negative 1/2, then time 2 times 3, which is 6. So that's an example on the rate of change, related rate of change problem, right? Normally, you are given for sure lots of quantities, either 2 or 3, and then you need to build up the relation between the quantities, right? The equation, you have to figure out the equation, and then you differentiate the equation about time t, because all the quantities are time t, right? Are function of time t, right? Then you just solve for the rate of change you are looking for, right? Really. Now let's see one more example. What's the example? The example here is we have a balloon. Air here is being pumped into a spherical balloon, right? This balloon here is in the shape of a sphere, right? Spherical balloon. And its volume, we know that its volume is getting bigger and bigger for sure. Its volume is increases at a rate. The rate is given, which is 100 centimeter cube per second, right? Now we want to know how fast is the radius of the balloon increasing when the diameter is 50 centimeter, right? So this is a problem here. We are given a spherical balloon. We want to pump air into the balloon. The rate of change of the air going in is 100 centimeter cube per second. And so the balloon is getting bigger and bigger. We want to know that when the diameter is 50, right? Which means radius is 25, right? We are looking for the rate of change of the radius, right? So there are two quantities. One is the radius, the other one is the volume, right? Volume is changing. We know the rate of change. We want to know the rate of change of the radius. their relation here for sure is natural. So let's write down our notations first, right? V here is the volume of the balloon. R here is the radius of the balloon. We know that dV over dt is given, right? By our given assumption, dV over dt is 100 centimeter cube per second. We want to find dr over dt when r is 25, right? Because diameter is 50, radius for sure is 25 centimeter, right? We want to make the connection between v and r for sure. By their relation, we know that v here is 4/3 pi times r cube. Right? That's the volume formula for a ball, right? And so now let's try to differentiate this equation above time t. Both volume and radius are function of time, right? That's our assumption at this point. So we get dV over dt is 4/3 times pi times 3 times r squared times dr over dt. So we use what? We use the chain rule here. Outer function is to the power 3 power function. Inner function is r. We don't know the function form, right? And so we are looking for the r over dt, plugging all the conditions. So when r is 25, dr over dt dr over dt, right? This is a term, this is the quantity we are looking for. This is 100 over 4/3 pi times 3 times 25 squared. So this is the rate of change of the radius when the radius is 25, right? So that's basically how do we solve this problem.